Hello, everyone. We're working through an introduction to statistical methods and data analysis by Ott and Longnecker, Chapter 14, Part 2, Factorial Treatment Structure. So in a factorial treatment structure, we are going to examine the effect of two or more explanatory variables on a response variable y. And we're going to consider all the factor level combinations of the independent variables. So suppose we already have our subjects. And then for factor one, let's suppose there are three levels. So level 1, level 2, level 3. You're going to randomize them in factor 1. And then suppose that factor 2 has two levels in the treatment, level 1, level 2, level 1, level 2, level 1, level 2. We're randomizing at this stage as well. And at the end of the day, we're going to observe some response variable. So when we think about this factorial treatment structure, essentially for every factor, you can multiply the levels to find out the number of unique treatments. So in this case, if we have 3 levels under factor 1 and 2 levels under factor 2, then altogether we have 6 different treatments. And you can see the combinations there. All right, one thing that you might be asking in this factorial treatment structure, if the effect of one factor on the response changes for different levels of the same factor. So essentially, if we have no interaction, let's look at factor 1, okay? And you have the response. So here, if there is no interaction, then you might see that as, let's suppose there's 3 levels, right? So let's suppose we see a low, a high, and then low. So this is factor 2, level 1. Okay, and then if I did a similar plot, and what ends up happening is that level 2 of factor 2 has a similar shape, then we'd say there was no interaction between factor 1 and factor 2. However, if we looked at factor 1 and the response, and we saw something that looked like this for factor 2 level 1, but then we saw something that looked like this then we would say that there was an interaction, because the relationship between the different levels of the factor and the response changes based on what we saw on factor 2. So how do we model this? We're going to use a linear model where we have yijk equals mu ij plus epsilon ijk. So yijk is the response from the kth experimental unit. If we're talking about people, then these experimental units are subjects, receiving the ith level of factor A and the jth level of factor B. So in our previous example, people were randomized and there were 3 levels, right? Level 1, level 2, level 3, this is factor 1, or we'll use factor A. And then for factor B, level 1, level 2, level 1, level 2, level 1, level 2, and people were randomized, right? So essentially here, I goes from 1 to 3, and J is only 1 or 2, right? All right, so mu ij is the treatment mean for the ith level of factor A and the jth level of factor B. Okay, so for example, mu11 would be the mean for the group that got the level 1 treatment for factor A and the level 1 treatment for factor B. We could break down this mu ij by doing this. So you could either say yijk is some overall mean for the ij treatment plus the random error of the ith level of factor A, the jth level of factor B, and the kth person or the kth experimental unit if you weren't talking about people. Or you could write the model as yijk equals some overall treatment mean plus the effect due to the ith level of factor A plus the effect due to the jth level of factor B plus the interaction effect tau beta for the ij treatment and plus epsilon ijk. So either one of these is appropriate for writing out the model. Now, if we thought about the epsilon ijk, that's the random error associated with the response from the kth person receiving the ith level of factor A and the jth level of factor B. Those are independent and identically distributed as normal random variables with a mean 0 and a variance of sigma squared epsilon. So if we want the expected value of yijk, right? Well, that's just the expected value of mu plus tau I plus beta j plus tau beta ij plus epsilon ijk. And that is equal to mu plus tau I plus beta j plus tau beta ij plus the expected value of epsilon ijk. Well, we know this expected value is equal to 0. So you're just left with the mean for the yijk's, mean mu plus tau I plus beta j plus tau beta ij. All right. Similarly, we can find the variance for the yijk's, and since mu, tau, beta, and the tau betas are all fixed and known constants, we can say the variance of yijk is just going to equal, well, the variance of a constant is 0, so that's just going to equal the variance of epsilon ijk. We know the variance of epsilon ijk is our sigma squared epsilon. Okay, so now we have the distribution of our response being a normal random variable with that mean and variance equal to sigma squared epsilon. Okay, so there's a lot of notation. Don't let all the notation worry you too much. Because essentially you're going to just calculate this using some software package, either R or some other software that you prefer to use. We're going to say, suppose we have a completely randomized 2-factor experiment with A levels of factor A and B levels of factor B and N observations on each of the AB treatments, right? So essentially we're in a situation where we have level 1 all the way down to level A, and then we have level 1 all the way down to level B. 1 all the way down to level B. So altogether, there are A, B treatments total. Okay. So YIJK is the observation of the kth person receiving the ith level of factor A and the jth level of factor B. That's our YIJK. The Y bar I dot dot, right? This is the sample mean for the observations at the ith level of factor A. So what we need to do is we need to sum over the J and K's to be able to obtain the Y bar I dot dot. If we want the Y bar dot J dot, that's the sample mean for the observations at the jth level of factor B. So essentially we can sum over the I and K, and that will essentially give you that sample mean that you're looking for. And if you want the Y bar IJ dot, that's the sample mean for the observations at the ith level of factor A and the jth level of factor B. So we just need to sum over the K's and of our YIJKs and divide by N. And then if you want Y bar dot dot dot, that's the overall sample mean. So you need to sum over the I's, the J's, the K's, and divide by ABN. Okay, so to obtain the estimates of the parameters, these are some facts of our model. That must be true. But then we can get our estimates for our we can get our model estimates. So remember that our model looks like YIJK equals mu plus tau I plus beta j plus tau beta ij plus epsilon ijk, right? So essentially we want to get all of our predicted values, right? So when we do this, we can say, okay, if we want to get the predictions, right? We want the y hat ijk, well, then we're going to need the mu hat plus the tau I hat plus the beta j hat plus the tau beta, the interaction term hat. And from there, just as always, once we have these estimates, we can calculate the residuals. So remember that the residuals, right, are just equal to the observed y's minus the predicted y's. And with some mathematics, right, once you plug in the observed minus the predicted, you can distribute that negative sign. And some things are going to end up canceling out, right? So our residuals come down to an even easier formula, which is that our residuals are equal to the YIJK minus the Y bar IJ dot. Okay. So just as always, we're going to partition the total sum of squares, and partitioning the total sum of squares will help us in when we want to build an ANOVA table. And so what we're going to do is we have the total sum of squares is equal to the sum of squares due to factor A, the sum of squares due to factor B, those are our main effects, plus the sum of squares due to the interaction term AB, plus the sum of squares there. Okay, so when you look at all of these pieces, this piece right here is our sum of squares due to A, our sum of squares due to B, this piece here is our sum of squares due to AB, and this piece here is our sum of squares there. All right, so what we can do then is we can create an ANOVA table for the factorial treatment structure. And this has a similar format as before, right? We have what is the source of the variation? What are the associated degrees of freedom? What are the actual sum of squares equal to? What's the mean squared equal to? We can calculate an F value for our main effects as well as our interaction term, and we can calculate a P value. So we're going to go into more detail of how to conduct this in R in a future video, but You could hypothetically conduct this by hand, but I just want to say that there's not really a benefit to doing this by hand, especially as your sample size increases. Doing this by hand gets harder and harder and harder. So I hope you learned something about the general structure of when to use a factorial treatment structure. Remember essentially that people are randomized on 2 separate variables, and then that gives you this factorial treatment structure. And then you're going to compare, is there an effective treatment? Is there an effective factor A? Is there an effective factor B? And is there some sort of interaction happening between A and B that we need to be concerned about? I hope you learned something today, and I'll see you in the next video.